So, in early classes we looked at the effect of alloying elements, how the alloying elements segregate during solidification, and that can lead to the embrittlement of the weldments. So, we looked at the effect of carbon, silicon, aluminum, as well as the phosphorus segregation on the grind boundary during solidification of the weld microstructures. Especially in resistance spot welding, it is very significant, right. So, now when you look at the partitioning, and we look at carbon partitioning, phosphorus partitioning to the solidifying liquid at the weld center line, as well as the weld primary solidification grind boundary as well as secondary grind boundary, and that can lead to embrittlement. And we looked at the adding the other beneficial alloying elements. For example, in order to control the phosphorus segregation, how boron can be very useful, because when you add boron, and boron stops the phosphor atoms coming to the interface between the solid liquid and the grind boundaries, and thereby we can reduce the phosphorus segregation. And we looked at the results of that the experiments where the boron addition can effectively reduce the phosphorus migration, thereby improving mechanical properties. But now the addition of boron or changing the chemistries, it is not always viable, and because that is actually still development work. So, what happens if you are given a microstructure, if you are given a composition, whether we can modify the weld thermal cycle in such a way that we can avoid this embrittlement problem. Can we mitigate the welding process in such a way that we can reduce the segregation of these alloying elements, and thereby can we reduce the embrittlement. I am going to show you it is possible to do to modify the weld thermal cycle, as well as to improve the mechanical properties by this modification. We look at the same example steel what I talked about in earlier in one of my lectures. We have steels of a very carbon 0.07 with a very increasing very large amount of phosphorus, which is not conventionally added. We just added it just to show whether it is possible to generate advanced ISM steel with high amount of phosphorus. Okay, so we looked at the effect of the phosphorus and boron on the segregation behavior, and we look at one case. For example, only steel CP. It showed the partial plug failure, right. So, because of the phosphorus segregation. So, now we need to make sure that this weld of the steel CP does not fail in the weld zone. So, we can add boron to avoid the failure of the weldments at the interface in order to achieve the full plug failure. But now the steel chemistry is fixed. Say for example, we have only steel CP, we cannot add boron. Can we modify the weld thermal cycle in such a way that we can improve the mechanical properties of steel CP? Okay, it is possible. We will look at one modification in weld thermal cycle. Before that, I will explain how this modification can be carried out. So, this modification we can do that by applying a second pulse during resistance spot welding. So, in conventional single pulse resistance spot welding, what we do is again recall our lectures in resistance spot welding. So, we have the current cycle where we give an amperage of over 5.5 to 6 kiloamperes, and we can recall that we can identify the actual current the amperage from the weld growth curves. We can identify, we can apply an amount of load required to keep the faying interfaces together, and then we can play around with the pulsing parameters and to achieve the varying weld nugget size, right. So, now we instead of doing a single pulsing, in order to reduce the segregation, or in order to homogenize the alloying elements in the weld nugget, we can also apply a second pulsing. So, instead of having only a single pulse, we can also apply a second force pulsing, and whether it is going to improve mechanical properties or not, we will see in subsequent slides. Right now we see that the effect in the welding parameters. So, instead of using a single pulsing, we do a double pulsing. In double pulsing, what we do is in a single pulsing we have a single current pulse is given, and by giving this pulse and the load, we achieve a weld nugget of, say for example, so and so diameter. We get this is a weld nugget diameter, weld nugget, right, in the resistance spot welding. So now instead of giving a single pulse, after a first pulse, and we will also apply a second and current pulse as shown over this figure, and by doing so we may also remelt with the first nugget which is formed during first pulsing, and that can influence favorably the alloying element which are actually segregating at the weld center line. Okay, we will see in the subsequent slides how we can do that. So what happens in single pulsing? So single pulsing we generate an weld nugget. So this is sheet 1 top sheet, and this is bottom sheet. So when you are applying using an electrode, we pass a current, and we also apply a load, and doing so we melt the interface and form what is known as weld nugget, right? And these regions are the heat affected zone regions. And during this first single pulsing, what happens? So this is the weld nugget, and this is HZ, what you see over here, and this is the base material. And if you look at in somewhat higher magnification, you see very clearly the columnar grains which are actually grown from the fusion boundary towards the weld center line, and during this process the alloying elements are trying to segregate at the weld center line, because that is the region which solidifies at the last, right. So when the grains are solidifying from this direction, you will have a segregation at the weld center line. Because of the solidification of this liquid over here, it takes place at the end, and the alloying elements such as carbon, phosphorus would be migrating towards the weld center line when the solidification happens from the fusion boundary. Okay, so now if you apply load to this microstructure, so when you are doing a cross section test, for example, when you pull apart these two regions, so what will happen? So this is the region where you expect a failure, a crack to nucleate, because that is the interface which is there, and you also see this interface is like a notch, isn't it? So this interface will act as a notch, and then there will be a stress concentration here at this point when you are pulling along in a tensile direction along this as shown in this figure, and obviously you will have stress concentration, and then you will have a crack propagating along this weld center line. And then if because of the brittle elements that are segregated at the weld center line, and you will have a crack propagation, and then if you have a high amount of segregation, you will have a complete interface failure. So if segregation is minimal, or if you don't have any detrimental element like carbon, phosphorus, then you may end up having cracks going like this, because the microstructure over here is very strong, right? This is martenseric microstructure, and you will end up fracturing at the heat affected zone. That is very good, okay. But because of the segregation of alloying elements at the weld center line, you most likely, if you have carbon phosphorus segregation, and you will have a crack propagating from at the tip of the fusion boundary and going towards the weld center line. Say for example, you expect a crack to happen, nucleate at this region and propagate, and then moment it reaches a critical limit, and because of very strong segregation, you will have a failure of the plug, okay, whether it's partial, and if you have a high segregation, you will have a complete interface failure where we have a plug ratio of 0. Okay, so now what happens to the single double pulsing? In double pulsing, and what we do is we also have an additional pulse, current pulse is given apart from this the first pulsing, which is actually used to make the weld nugget, right. In the second pulsing, so this is the first pulse, and you would the first pulse area, so what you over here, and this is the first pulsing, and because of the second pulse, the current you are given, you remelt some of the regions inside the first pulse, and the nugget which is created by the first weld. So this is the primary weld nugget, and this is the secondary weld nugget which is formed after the second pulsing. This is clearly seen from this image, where you have the primary weld nugget which is formed from the first pulsing, and then after applying a second pulsing, you will have a second melting of the weld center, and then you have a secondary weld nugget that is formed after the second pulsing. And this can be beneficial and because of the basically what you do here is applying second pulsing, you do a heat treatment. Okay, you do a heat treatment of the weld nuggets, which is actually formed by the first pulsing. Okay, so you apply a second thermal cycle which can do a homogenization of the regions somewhere over here, for example, or because of remelting you may also have segregation effects reduced in the regions. We will see in the subsequent slides what happens in chemically and when you are applying a second pulsing. You clearly see in the curves where the mechanical properties certainly improve. For example, the blue curve here, it shows the cross tension tensile stress tensile test results, where the first pulsing it shows very poor strength, whereas after applying a second pulsing your strength level increases significantly. You also have a high displacement. That is that means that the mechanical properties improve significantly. So you will see in the first pulsing case, the blue case, what you see over here is the failure nucleated at the interface from the heat affected zone, and then it propagated along the weld center line, and then the failure of the plug happened in a partial plug way mode. So the crack propagated and then it failed and then it broken. It has broken at the middle of the weld nugget, and this is not advisable failure mode because you have a plug failed. And in the second case, when you have a double pulsing and you see that strength is increased and displacement also increased, that means the mechanical properties are improved significantly. So if you look at the failure mode, so the moment you have a failure initiated, and then the regions where you see a boundary between the primary and secondary weld nugget, boundary between the secondary and primary weld nugget. So these regions, the moment your crack reaches that region, so what happens? The crack is deflected. That means that your weld nugget is intact. Majority the secondary weld nugget is intact. So you improve the mechanical properties significantly by doing a second pulsing. Okay, and then second pulsing increased the plug size as well. So you increased significantly the plug size. The plug is intact. You see that the plug has come out intact. Almost 80% of the plug is intact. That means that it is much more acceptable failure mode compared to the single pulsing case. But there is no significant variation in the harness in both the cases. In both harness showed, that means that showed similar harness variation. That means that no mechanic, the harness wise there is no problem. But we have a significant improvement in the failure mode as well as the mechanical property. That means that second pulsing is beneficial to improve the mechanical properties. But how does the second pulsing help in improving the mechanical properties? That's a big question, right? We need to understand what happens when you apply a second pulsing. So for that we'll have to look at the thermal cycles, and subsequently how the thermal cycle, the change in thermal cycle is leading to change in the segregation of alloying elements in the weld zone during single as well as double pulsing case. So first we'll begin with the thermal cycle. So these are all calculated thermal cycle using an FEM simulations. So if you have a single pulsing, what we do is at the weld center, so the temperature reaches much above the liquidus temperature, and subsequently you cool to room temperature. And weld center and weld edge, based on the peak temperatures, you may end up having either melting or heat affected zone. Right, in weld edge, the melting point is below the peak temperature reached during welding is below melting point, whereas in weld center the peak temperature reached is much above melting point. So you will end up having the molten regions between the weld center and the weld edge. Okay. In a single pulsing, we are not doing any heat treatment. So from the peak temperature, material is the weld is cooled to room temperature, and because of double pulsing, and instead of cooling after you're forming a molten region, so you cool it to some temperature, and then because of second pulsing, the material is again heated up to another temperature, and subsequently upon heating up, we cool to room temperature. So we modify the thermal cycle from continuous cooling from liquidus temperature, and the weld center upon cooling to some temperature will again heat it up like in a post weld heat treatment. Okay, so we will again heat it up and then subsequently we will cool to room temperature. It same happens at the weld center as well as the weld edge. Only thing is in the weld's edge, the peak temperature reached in the pulse cycle is also lower, and we will also have effect of peak temperatures seen very clearly by comparing the weld center and the weld edge. Okay, so it's very clear, right? So in a single pulsing, we are cooling continuously from solidification temperature to room temperature, whereas in double pulsing, instead of cooling to room temperature, upon cooling to say some temperature where we have a complete solidification, and then we increase the temperature to slightly higher, and then subsequently we cool to room temperature. And this increasing temperature can cause a very positive effect by homogenizing the microstructure and the composition, which we already saw in the optical microscopy because of this reheating, and we form secondary weld nugget. So this is the first weld nugget, sorry. And because of the reheating, we have melting at in the regions, and we form secondary weld nugget, and because of this heating, right? And we look at how the alloying elements segregate during this process. So we can simulate again, and I will show you the results of the simulations, which we can use it to understand what happens to the alloying elements during this post pulsing or post weld heat treatment. So again we look at the microstructure evolution. So we have simulated the similar weld thermal cycles where we have in both the cases weld center and weld edge, we cool to some temperature and subsequently we take it to other temperature. So in a single pulsing case we will continuously cool to room temperature, whereas in double pulsing case, so instead of cooling to room temperature we will take it to again to some temperatures and then subsequently cool it back to room temperature. Okay, so at time t0 everything is liquid, right? It's weld center. So everything is liquid over here, you see here, and then you will have a uniform distribution of carbon, manganese, silicon, phosphorus in the liquid. It's a single phase liquid, right? So when it's liquid, all the elements are homogeneously distributed. And then when you start cooling down, after the current is passed, if you switch off the current, the pulsing is completed. When it cool down, say for example when you reach a temperature of 1600 Kelvin and you have a partial solidification of the delta ferrite. For example, in this case we have a delta ferrite as well as the austenite forming. Okay, and during this process what happens, because of the solubility difference between delta ferrite austenite in the liquid, and you will have a segregation of carbon and phosphorus manganese, silicon at the interdendritic boundaries as well as at the liquid front. Okay, so you will have a segregation based on the solubility of the elements in delta ferrite and austenite in liquid, and you will have a segregation at the interdendritic boundaries as well as at the solidification front, because that is the region where the carbon atoms are migrating from the delta ferrite to the liquid. Okay, and subsequently if you cool further and your solidification is getting completed, and you will also have the segregation becomes very predominant. For example, at this case you still have some liquid is left at this weld center line. For example, in the simulation shows this is a fusion boundary and this is weld center line, and you already see that in a weld center line the carbon concentration, if you begin with 0.07, but the carbon concentration can go up to 0.58%. Similarly, manganese can go as high as 0.5 and silicon up to 2%, and the phosphorus can also go up to 0.158%. Okay, and subsequently if you cool down, at this point the solidification is completed, and you see a significant amount of segregation. That's the weld center line segregation we always study, right? So weld center line is now enriched in carbon. Carbon concentration is as high as 0.5, even if you begin with 0.5. So this is the region where we expect an interface failure to happen at the weld center line. So now, in our case, we have a secondary pulse. We are given second pulse, double pulse is given, and during this process, instead of cooling to room temperature, what we will do? So we are now taking again whatever solidified to another temperature. Okay, so again we are heating up to another temperature. You already see there is a homogenization. You see homogenization happened from at the weld center line by carbon and phosphorus segregation is really reduced. You see that in previous graph. For example, in this graph you see the carbon concentration is enriching, whereas if you heat it up, instead of solidifying to room temperature, cooling to room temperature, if you heat it up, you see the carbon already is homogenizing. Okay, similarly phosphorus also homogenizing because of the second heating, and subsequently if you cool down, you will also increase homogenization because still the material is in very high temperature, right? So it will be about 1300 to 1600 Kelvin temperature. So what is the result? Actually we are seeing that in the only single pulsing, in the experimental result also we see segregation of phosphorus, silicon and manganese at the boundaries, dendritic boundaries. You see here in this picture, you see at the dendritic boundaries the manganese are all enriching the boundaries, silicon is enriching as well as phosphorus also enriching the solidification boundaries at the center as well as the edge. And you see the calculation results, what I showed you in previous slide also. You see the clear segregation of phosphorus, manganese, silicon and manganese at the dendritic boundaries, which is clearly seen also in the experiment by the elemental mapping, electron probe microanalysis mapping. And the same is actually shown at the edge region, and you also see a segregation of manganese, silicon and phosphorus at the grind boundaries. You see the bright regions, they are all segregated regions which are nothing but the dendritic boundaries during solidification. Surprisingly, if you look at the elemental distribution at the edge regions, after double pulsing, after the second pulse, you see already the regions are all homogenized. You see that there is no distribution. The phosphorus is distributed very homogeneously. Similarly, the amount of manganese at the weld center line, you see it's a decrease significantly. You see that regions. That means that the double pulsing indeed homogenizes the segregation which actually formed, and it will also become clearly seen from the EPMA line scans at various regions. This is the experimental line scan during the second pulsing. So for example, line scan is carried out somewhere here, somewhere over there, for example somewhere over here during single, after single and double pulsing. You see clearly the manganese is segregating in some regions. Those regions are all the boundaries. Similarly, silicon is segregating and phosphorus is segregating at the boundaries. Whereas after double pulsing, you see that phosphorus, silicon as well as manganese is more or less the same in almost all the regions. That means that the segregated regions at the grind boundaries are all homogenizing. And that's what's also shown from the simulation results. In the simulations, what you saw here is the segregation of manganese, silicon and phosphorus during single pulsing, whereas in double pulsing you see that the phosphorus is completely homogenizing after the second pulsing, which is the effect is very significantly seen in the phosphorus case. That means that second pulse helps in avoiding the segregation of phosphorus particularly, which is actually very beneficial. If you don't have phosphorus segregation and your embrittlement decreases significantly. And the results of cross tension test we already shown in the previous slide. After double pulsing, the strength is increasing compared to the single first case, and also the failure mode, the plug ratio what is plug ratio? Again, recall from my previous lectures the size of the plug after the testing and the size of the weld nugget, the ratio of that, and after the double pulsing the plug ratio is also increasing significantly. Okay, and that is mainly due to the reduction of phosphorus segregation after double pulsing. So the phosphorus segregation decreases significantly at the grind boundaries at the weld center line, leading to the improved mechanical properties. So that means that so you don't need to change the chemistry. By carefully manipulating the weld thermal cycle, we can still improve the mechanical properties of advanced iron steels. That's the lesson I want to give you, and this understanding is possible mainly because of the calculations and the understanding of the elemental behavior during welding. So that is the lesson I want to give you for you, that it's very important to understand the physics behind the process, how the segregation happens during solidification, and once you understand the fundamentals, what I explained in this lecture very clearly, we can improve the mechanical properties of these welds either by modifying the alloying elements or by changing the weld thermal cycle. So in this case, for example, what you have done is we change the weld thermal cycle instead of using single pulsing, using a double pulsing, and double pulsing leading to homogenization of the alloying elements, especially phosphorus, and but thereby reducing the embrittlement at the weld center line and the grind boundaries. So the lesson I want to give you from these lectures is, conventionally what we are doing is we do resistance spot welding, okay, and then you look at the thermal cycle, what thermal cycle is you are going to apply, and then the microstructure, analyze the microstructure, and investigate why the weld is failing. But now what you have done, what you need to understand is, now you first to make yourself comfortable with the physics, the metallurgy of these advanced iron steels during welding. So once you understand that, and instead of playing around with the welding parameters to get the better mechanical properties, you know that what microstructure you want, what segregation, how homogeneous the elemental distribution should be, and then we can understand the microstructure evolution and which microstructure thermal cycle can give you this homogenization, and subsequently you can have a thermal cycle predicted, thermal cycle which can be predicted to get these microstructures. Ultimately you will have using that thermal cycle best microstructure. So instead of playing around the welding thermal cycles to get the better mechanical properties, and you identify the mechanical properties and the microstructure and the elemental pattern, elemental segregation behavior, which can give you the mechanical properties. Once you know that, we can get thermal cycles needed to get you these mechanical properties. So this is with this I like to conclude this lecture series. So the lesson I want to give you is, it's very important to understand the physics and metallurgy of advanced iron steels. By understanding the physical metallurgy and the fundamentals of the alloying elements behavior, and the welding thermal cycles can be identified to weld these steels, and we can achieve the best weld from these steels, advanced iron steels, by carefully understanding the microstructure evolution and the correlation between the weld thermal cycle and the microstructure. I also acknowledge some of my colleagues who actually helped me to generate these results from the Delft Institute of Technology in Netherlands. I will also acknowledge my students who helped me to organize these slides and to help you when you are doing this course through various forums and emails. Thank you.